Recording's rolling. It is Monday, August 25th. So you guys have your laptops. Back on Friday, we're doing the Aleks initial knowledge check. You're about halfway through, so we'll give you guys today to keep working on that. Right. So, great. I got a demo for you guys. This will take you a few minutes. I'll show you guys how to work this, but this also involves a little bit of math, a little bit of math, a little bit of science. You guys see that shit doing today. I'm going to get you guys your book today. It looks like this. Now it's in two halves. So you guys got Florida Reveal Algebra 2. You guys give the course as Volume 1. That's going to correspond to Semester 1. There's also a second half, which I'll give you probably in January. I think make those. So guys, this is a paperback book. When I give this to you guys can keep this. You don't have to turn it in at the end of the year or anything like that. You can write in it.
Yeah.
Okay. So we're gonna get going on this seriously. So at least next week, I'm kind of planning that. I think on Monday would be a good. Oh yeah. Okay.
We need to bring that with us every day.
Yeah, have this. Yeah, again, starting Monday, really, like start Monday. Yeah, have this. Okay.
You can't put it in your flash.
Huh?
You can't like put it in your flash.
I know. Well, you might need to take this home and do some assignments sometime. So yeah. So anyway, I'll be getting that to you guys today. Now, as far as the fast test, I know almost everyone in here is taking the fast test. There's a couple of exceptions. So I have a bunch of Algebra 2 classes where I'm going to have like 2 students in them. So kind of planning more than just be a fast kind of day. Wednesday, Thursday, have an activity lined up. And then I've been promising you guys a quiz on everything we've been doing up to, well, about nowish. So yeah, let's bump that to Friday. I think it's a good day. And then next week we'll get going to everything on Module 1 for your book. All right, so let's look at this triple beam balance. I just got this over the weekend. So way to measure mass. And I was talking about this with my physics classes. I'll tell you guys too. This is good to know for a few reasons. So how can this measure mass? What is mass? Oh yeah, go ahead.
What would the quiz be on? Is it just algebra overview?
Yeah, a lot of it is. Guys, anything that we've been doing in class, if you've been paying attention, follow along. Guys, that Algebra 1 review packet, if you want it back, you guys are the class with the blue tabs back there. So it's back in your folder. So you guys have the Algebra 1 packet back. Okay. Okay. So let's do a little bit of physics here, a little bit of physics. Okay, we got this lab weight. This says 1,000 grams. That's also called 1 kilogram. So if I do this type motion with it, do you think it takes it has some resistance to change in motion? I can kind of feel that.
Yeah.
Right. Now what if I took this to the moon? Guys, take it to the moon. Would this feel equally the same on the moon?
No.
To do this with it? Who says yes? Yeah. Guys, this would feel exactly the same on the moon. Exactly the same. Now, what if you did this? What if you pick it up? So heavy. And then you take it to the moon. Is it a lot easier to pick up on the moon? Yeah. Because that's something different. So, guys, when I do this, I'm getting a sense of its mass or its inertia, its resistance to change in motion. When I pick it up, I'm lifting it against a force, which is its weight, right? Those are different concepts with different units, right? Also, mass is a scalar quantity, so it doesn't even have a direction to it, but weight does. Right? Weight's pulling straight down, and I have to lift straight up. Okay. So then there's one concept of the way. How can I say how much mass does something have? Now, there's different kinds of scales. There's like a bathroom scale you can stand on. There's scales with springs. And then there's this one, which works on a seesaw method. Now, it doesn't all fit in the screen, so you have to use your imagination a little bit, but I'll show you guys this. All right. You guys see how, this has like a seesaw motion? You guys see that?
Yeah.
And right here, this needle could point to like 0 if it's all leveled out. It could go above 0, it could go below 0, but if it's all evened out, it'll be point right to 0. Right, that needle will be. Okay. I can take a lab weight. This one says 147.5 grams. I don't think that shows up on the camera, but it says 147.5 grams. I can put it right here on this plate. Boink. Right, and then the whole seesaw goes clunk, like to the left or counterclockwise if you like. Okay. And then I got these 3 sliders. You guys see these 3 sliders? So hence triple beam, because these 3 beams. And I can slide these around to restore balance. I'm going to take this off for a moment, just show you guys what these look like. So this middle slider moves 100 grams at a time. Okay, you got 100. So you guys see there's 100. There's 200 right there. All right, and it's got this little notch in it where it locks in place. So once I get it, I have to pick it up to slide it over, and then it'll lock in place. So I'll move this to 100. This back one moves 10 at a time. It's also got notches where it'll lock in place. Move this to about the 40. All right, lock right in there, 140. This is 147 point something. So right now, It's still a little bit heavy. It still tips to the left. And I got this last slider that just moves 1 gram at a time. I think you guys can read that 1, 2, 3, 4, 5 gram. So I slide this over, slide over, slide, 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 and we get to the about the 7.5 mark. That's where this needle on the right side zeroes out. Again, gravity's pulling down, so the camera's the wrong angle. But from the side, when I moved up to 147.5, then this goes like this, goes whoosh, right, and then it hovers right at the zero. Okay, so that's how you know this is 147.5 grams. Okay. Now, guys, what do you think? What if I took? Did my screen freeze? Oh no, we're back. Okay, guys, what if I take this whole system, this lab weight, this triple V balance to the moon? Is this still going to read 147.5 grams on the moon? Who thinks it does? Who says yes? Who says yes, it does? Yeah. Turns out it does. Now, not all scales will, like maybe a bathroom scale wouldn't, but this will. Okay. If you had your weight measured at the doctor office, they probably use some of this. So I want to draw this out. Tell you guys a little bit of physics today. I might do that some days, and then this is going to turn to a math puzzle that you can solve with a little bit of algebra. And it's one reason I'm showing you. So I got this seesaw type setup. Okay? Suppose I have a seesaw, and maybe I have it balanced at its center. So they're going to prove the point. And I'm actually about to set that up right here. You guys see this ruler right here? This is about to be my seesaw. You see this? This is going to be my pivot point. So I can put this right here, and it just balances right about the 15 centimeter mark. So I can go like here, go plunk, falls off to the right. If I do this way, plunk, falls off to the left. But if I put it right at the 15 centimeter mark, yeah, right there it balances. See, it's all balanced right there. Right. Now you can take advantage of this to determine any unknown weight or mass unit, depending on your perspective. Right. So let's say you have one known weight and one unknown. So I got a couple right here. So this guy's 20 grams and this guy's 50 grams. Let's say I only know the one that's 50 grams. It's got a little number stamped on it. It says 50 grams. Let's say I'm allowed to know that one. What if I don't know what this one is? And I've actually used this process I'm about to show you guys right here a number of times in my life. So this could be pretty useful. Okay. So what I can do is I can put these on my seesaw and slide them around until it balances. Okay. If I do it this way and I let it go, it's going to fall off that way. Okay. But I can slide these around until it balances. Oh, yeah. Okay, so let's see. Okay, so it's going too much this way. I need to slide this one a little bit this way. Okay, a little bit more. Just feeling it. Like if I let it go, it's gonna go the wrong way. Ooh, close. Right. I'm getting real close. Okay, a little bit more, it looks like. Okay. That's a little bit more. Okay, it's like right about there. Right about there. Right about there. Okay. So it looks like my 50 gram mass is sitting right on the 20 mark, and my 20 gram mass is sitting about the 2.5 centimeter mark. Okay, so let's try that out. So I got this. I know this is 50 grams right here. Okay, and then I have, well, remember this one, I'm going to pretend I don't know, so I'll just call it M for mass. And let's say I want to solve that. It's going to turn into an algebra puzzle. And we're going to see if the answer is about 20 grams or so. Make sure that actually balances. Yeah, that's, no, hold on. This is, well, maybe it's closer like it's about 2 centimeters. Yeah, about 2. I'll call it the 2 centimeter mark right there. Okay, so this was at the 15 centimeter mark. This was about the 20 centimeter mark, and this was at about the 2 centimeter mark. Right now, I have not tested these numbers ahead of time, so we'll see how close this is. We're gonna see. Okay, and it balances there, and somehow I can use the fact that it balances to figure out what is this on my math right here. And the physics principle that this goes through is something called torque. You write that down. Torque, okay? Which is Greek letter tau. And it comes with this expression, R cross F. Okay. R stands for radius, F stands for force. Okay, guys, here's one place you use torque every day, is to open a door. Okay, so why put the door knob opposite of the hinges? Why not put the doorknob right next to the hinges? What if you had to do this? You're trying to get out the door. Would that be really hard? That'd be really hard, wouldn't it? Okay, what if the doorknob was in the middle of the door? Okay, that would be easier. But then if you put the doorknob on the opposite side, oh, you just put a little tiny force in it, it opens the door really easily. Not true? Right? So let's say relative to this pivot point right here. Okay. So I'm cut through some of the explanation, but just kind of boil it down to what's necessary for this right here. Okay. So relative to this pivot point, which is right in the middle, I have this radius on the left side, I call it R1. I have this radius on the right side, I'll call R2. Now there is a downward force from each of these. It's called a weight, and they're different weights. Right? So maybe like F1 and F2 get different forces, and that's resulting in different torques. Right? So this one on the left side tries to make the whole thing turn counterclockwise. I'll call it torque 1. This one on the right side says, no, let's go clockwise. I'll call it torque 2. So I got a torque 1 and a torque 2. And guess what those two torques do to each other? They cancel out? Yeah, they cancel out. Right? One's counterclockwise, one's clockwise. So you can say they sum to 0. So you can say the sum of the torque is equal to 0. Sum of the torque is equal to 0. Meter would be the unit. Or this R cross F here is equal in magnitude to this R cross F over here. So R1 F1 equals R2 F2. Here, I'll switch back to a black ink, so it's a little easier to read, but it's good, right? So my radius on the left side, well, guys, what's the difference between the 15 centimeter mark and the 2 centimeter mark? How long is this lever arm right here?
13 centimeters.
Yeah, 13. So in place of this R1, I'll call it 13 centimeters. Okay. For force, now I told you guys there's a difference between mass and weight. Now, it turns out weight is equal to mass times gravity field. So I'll say some unknown mass that I'm solving for times Earth gravity. Okay. Now on the right side, guys, what's the difference between 20 centimeters and 15 centimeters?
5.
5 centimeters. So that goes right here. 5 centimeters. Okay. And now I do know what this one is. I do know this mass is 50 grams. So I'll put 50 grams. That's a mass, but if I multiply by Earth gravity, that gives me the corresponding weight, which is a force. Okay. Now, guys, look on both sides. If you have Earth gravity on the left side and Earth gravity on the right side, what happens to the Earth gravity? Mathematically. Yeah, it cancels out. Okay, that's why I was saying, because back to here, this is basically a seesaw, it's the same method, right? That this would work equally well on the moon. It would give you an accurate reading on the moon, because it works on the same principle. So, now you do have to have some gravity to introduce a weight, but once you have a gravity field, it doesn't matter how strong it is, because it cancels out both sides. Right, so here, can you guys finish off this math? Remember, my goal is to get M equals. So I want to get how many grams is this unknown lab mass over here? Right. How would I solve that? It's algebra time.
Yes, keep happy.
It's algebra time. How do I do it? How do I solve? Okay, guys, I have 13 centimeters times M, and I'm solving for M for mass, is equal to 5 centimeters times 50 grams. How do I solve for M? Okay, yeah, you deal with this 13 centimeter coefficient?
Versus grams to centimeters.
5, eh?
Yeah, divide. Just divide 13 centimeters. Okay. Guys, grams and centimeters are two different concepts. Grams is like how much mass or inertia. Centimeters is like how long is a ruler. Okay. So those are different concepts. Okay. Right. But I have centimeters here and mass that's going to be in grams. And on the right side, I have centimeters and grams. So, okay, yeah, if you want to think in terms of units, which is also a good thing to do, what happens to the centimeters? Cancel out. Right. So it turns out this mass is equal to, we got 5 centimeters times 50 grams, all divided by 13 centimeters. And the unit centimeters cancels. And in the calculator, what's 5 times 50 over 13? That is 19.2 something something. So I'm getting a mass of 19.2, and the unit left is grams. Hey, look at that. Look at that. Because, again, I did not try this ahead of time, so I didn't, I just split it so the weights around until they balance. Okay? But the question was, what is this guy here? And it turns out it's 20 grams. Right? And I ran this method and I got 19.2 grams. That's really, really close. So I could definitely be happy with that. You guys get that? Yeah, and that's how a triple beam balance works right there. Right. All right. So Okay, you guys get rest of today to finish that initial knowledge check. By the way, if you finish this up and you still got a little time left, keep going on Alex because you guys know Alex is this open rolling program. You can just keep working on all year, right? And every quarter I have a goal for you guys. So at the end of every quarter, I'll put in a grade if you met the goal, right? So you can just keep going on this. Remember, guys, if you're if you don't know how to solve something and you ask me, I can come by and I'll help you out. I'll be happy to help you out. But keep in mind too that if you type in the correct answer, the program is going to assume that that means that you know the answer, you understand how to solve it, okay? And then it'll start asking questions that are on that level or harder, right? Versus if you miss it, it'll like, oh, okay, you don't understand that, so it'll start asking like easier type questions. It calibrates to each individual student, right? Oh, I also need to get you guys your textbooks, and yeah, that's about where we are right there. Right, so there's our goals. There's how a triple beam balance works.